Welcome back. In this lesson, we're going to look at the life of stars, for want of a better word. It's what stars are carrying on while they're being stars. What's going on in a star? How would a star develop? What are some of the thoughts of how a star would develop, and how would a star stop being a star? And so, as different stars have been studied in terms of their temperature and looking at them and seeing what kind of elements are coming out of these stars or are contained in these stars, these are the best ideas that we've come up with in terms of what's going on in the life of a star. So the first of all, we go back to the idea of a nebula. And the nebula, remember, was the dust and gases that are simply just existing in space, floating in space, but in themselves having mass. And since they have mass, they will exert a force on each other. And since they do, they will start to come together. They will coalesce into a massive collection of dust and gases that eventually will exert more and more gravity on itself. The closer that these particles are, the more gravity exists, the more the pull, the more the pressure. Okay? Eventually, that pressure in that cloud becomes substantial. And when you build pressure, you're also building temperature. So as the gases collect because of gravity, and more gas is able to collect, and of course the more gravity you have, the more gases can be collected still. And then that gravitational pull will increase the temperature, and eventually the temperature will create a nuclear explosion in the core of that star, and that becomes a star. If you think of that as the birth of a star. Now, what does that mean? Do we see stars being born? We see stars that are in nebula or nurseries. The Pleiades comes to mind. The Pleiades is in Taurus the Bull. There's 7 stars, very, very small stars that appear to have all come alive out of this field of gas and dust. So that would be the birth of a star. And then have we seen deaths of stars? Well, we have seen explosions, supernova explosions, and a lot of that has to do with how this machine of this star is actually working. So starting with the idea of an interstellar cloud of dust called a nebula, gravity pulls it together and the temperature rises, and right as it's about to become a star, okay, and where you have the nuclear fusion of hydrogen together to make helium, it's called a protostar. So proto simply means before or at the beginning of or initially. So a protostar is all the conditions are right so that with a little bit more temperature increase, you can start this nuclear reaction of taking 2 hydrogen atoms and pressing them together with enough heat and energy, enough pressure and gravity for it to fuse into helium. And when you do this, you release a ridiculous amount. It's a hydrogen bomb, essentially. That's what's happening on the inside of any star, and this is called fusion. So pushing atoms together to form bigger elements is called fusion, and this is what happens in a star. So as soon as this begins to happen and energy becomes released, the star starts spitting out electromagnetic radiation in the form of light, in the form of radio waves and heat and all the entire spectrum. And you've got a balance going on. You've got these explosions of thermal energy coming out, and you've got the gravity of the material that's being held together because of its mass together. And so you have this tension of outward force and inward force that keeps this star regulated, and it becomes a stable star. It is burning its fuel. The fuel is what it's made of. Okay, it's burning its fuel, and as it's burning its fuel, it's stable. It is staying in a context of outward expansion and contraction due to gravity, and it stabilizes into something that can last for a long time. It would become a main sequence star on the HR diagram. Okay, so if you burn through your fuel very fast, Okay, let's say instead of having a campfire, you have a bonfire. Okay, or instead of going to the grocery store, you go on a shopping spree and you're burning through your fuel. Well, you won't last very long because as soon as your fuel's gone, you're no longer a star. If you burn through your fuel very slowly and stably you'll last a long time. Okay, it's just conservation. So a small star that's burning fuel slowly might be something like, it might last something like 10 to the 11th, which means 1 with 11, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's see how long that is. Okay. Okay, so 1,000, million, 100 billion. Wow, that's a long time. Okay. Something that's going to burn through faster might only last like 10 to the 7. 1, 2, 3, 4, 5, 6, 7. Okay. So you see that's like 10 million years. Now, that's give or take whatever, because that's the idea of if you've got that much fuel and you're burning it at this rate, how long will it take before it's gone? If we can estimate how much of a star exists, like how much stuff is there, knowing that it's nearly all hydrogen, how long will that hydrogen last? Well, it's how fast it's burning. Okay, so 90% of the stars that we know of, 95%, are in these main sequence stars in the HR diagram. And then of that star, as people have thought this through, most of that time is going to be spent during this main sequence where they're burning it slowly and it lasts a long, long time. Okay, so what happens when you've burned all your hydrogen? Okay, so if you have a star made up of hydrogen and they've all been squeezed and now all turned into helium, and you have no longer any hydrogen to burn, what do? So helium is still a small element. Okay, it only has 2 protons. It also has 2 neutrons, so it's got 4 nucleons that have to be squeezed together. So it takes energy to do it. It takes more energy to squeeze helium together than it does to squeeze hydrogen together. So as that's happening, it's going to take more energy. So it's going to be burning fuel faster. All right. It also has to get bigger. So when you start burning these bigger elements, you will expand. And as it expands, it cools. All right. So the bigger it is, in order to do it, the more volume it takes up, the less intense the light is, so it becomes cooler. Okay, so it's going to go down towards the red side of rho G Biv, and as it uses up all of the last of those elements, I think the biggest element that you can burn or end up with would be iron. It can't burn iron. It can burn these lighter elements making into the bigger, but you can't just keep going forever. It eventually collapses. Okay. And when it collapses, all of its nuclear fuel, the gravity squeezes the star down, and you're going to end up with, instead of an enormous star, you're going to end up with a very small star. Okay, so we'll just trace this. Okay, so if you start with the dust and gas, the nebula that we looked at, and it turns into the protostar and then starts glowing, this is the main sequence star, like our sun. Okay, this is, remember, the HR diagram that exists here. If then you burn all your material, all of your nuclear fuel, it starts expanding. Eventually it expands to where it's burning, it can't burn iron. Okay, it can get higher, it can burn carbon, it can burn some of these mid-size elements, but it can't burn iron. When it gets up that big, it's going to collapse. And as it collapses, several things happen. Okay? You go into these variable stars like quasars and pulsars that are emitting lots of energy. It's unstable, okay, because it's not regulated like a main sequence star. Remember, you've got the thermal energy expanding outward, you've got the gravity pushing in, and it kind of stays regular. Well, in this case, it's falling apart. It's the house of cards is tumbling, and you end up with some kind of a squished star. It could lose some of its gas, like a planetary nebula, and then end up as a white dwarf, and then later even as a black dwarf. So what's happening, your size is changing, your color is changing, your temperature is changing, all of these things, and all of them, the type of star that you have can change. So this is the idea, what I mean, the life of stars. You've got red giants like Betelgeuse. it could blow up at any time and become a supernova. Or you've got other stars that are so small and very hot and very dim, like white dwarfs that we can find other places. And then you can even have neutron stars and things like this that are even weirder, and we'll look at that in a second. Now, how a star would end, I guess, is based upon how big it is. So little stars simply just collapse, okay? They will expand up to a red giant because they're burning these higher elements, and then eventually just squeak down and just kind of go out like a cinder. That would be a white dwarf. If you have a bigger star, okay, so that's like a half as big as our sun, up to about 3 times as big as our sun. As it expands, it loses gas and becomes a planetary nebula, and then eventually becomes a white dwarf. The massive stars, the huger ones, bigger than 3 times our sun, explodes in a dramatic explosion called a supernova. Okay? Even the Bethlehem star is thought to have been a supernova that you could even see during the day. For instance, if Betelgeuse, that star in Orion, explodes today, it's so bright that we could see it during the day. Like the sun wouldn't even obscure it. It's that bright. Okay? And then all that is left is this tiny little neutron star, or if it was big enough, it wouldn't just be a neutron star, it would be a black hole. And many galaxies are thought, even the Milky Way galaxy, has a black hole in the center of the galaxy. So as a final review, these lives of stars, you have nebula that condenses into a protostar and then starts glowing. That's a main sequence star, and it just burns out. If you've got a really little star, it just kind of squeaks out and becomes a white dwarf. If one like the sun, that's a medium-sized star, as it uses up all of its hydrogen, will get bigger and bigger and bigger, become a red giant as it's burning bigger and bigger elements, then eventually kind of slough off some of its gases, become a nebula, and eventually a white dwarf. But if you have ridiculously big stars, much bigger than the sun, as it becomes a giant, it won't just become a giant, it'll become a supergiant, and then supergiants, when they explode in dramatic fashion, and either become a neutron star, which is my favorite, or a black hole. And a neutron star would have like a tablespoon of a neutron star would have the same mass as our sun, or the same amount of stuff, but in a tiny, tiny place. So it's extremely massive, but doesn't take up a lot of space. So neutron stars are so awesome, cool. And then eventually, it's so much condensed that light won't even escape, and that's what a black hole is.